Hello, Professor Polytoad here, and let's talk about geology. Today, we're talking about rock formations that can cause some of the most interesting looking outcrops out there, and is arguably one of the best indexes of geologic time, sedimentary rock, and stratigraphic facies. For starters, sedimentary rock is one of the three main types of rock, and is produced by the accumulation of weathered rock material from other pre-existing rock. This material can range in different sizes from sand to mud to silt, and is a large determining factor in rock naming. For example, a sandstone would consist mostly of sand-sized grains, and a mudstone would consist mostly of mud-sized grains. This chart is used to help determine grain sizes and name the sedimentary rock. Stratigraphy is the layering of beds in sedimentary rock, and a bed is the visual layers of different grain sizes due to the accumulation of these sediments. These beds typically form underwater due to a majority of sediment deposition coming from water by being carried, in ways such as by rainfall or by rivers. To help me illustrate stratigraphy, I would like to invite my friend Crustle to come on. Crustle just so happens to live in a block of sedimentary rock showing the stratigraphic facies mentioned earlier. These are the layers present within this block of rock. There are a few laws to stratigraphy that help us understand what the rock is telling us, but the main one is the law of superposition. This law states that the oldest layers of rock, the ones that formed first, are the bottom stratigraphic layers and are overlain by progressively younger ones. Unfortunately, we don't live in a perfect world, so we can have cases where movement of rock has actually flipped these layers of sediments and caused the oldest layers of rock to be on top of the progressively younger layers. To check this, we can also look at the beds themselves to show the way up direction, in case it's not blatantly clear. During sediment accumulation, various different grain sizes are deposited at once, and it's not until settling of the sediments that the grains start to sort themselves and form the beds. As the grains settle, the larger grains, like sand, are much denser than the smaller grains, like mud, and will settle towards the bottom of the layer with the smaller, less dense grains accumulating at the top. If we arrive at an outcrop where it's not clear which direction is up, we can examine the beds for different grain sizes and determine the way up direction that way. Because Crustle has layered rock that is very flat, we can just assume that the oldest layers are on the bottom with progressively younger layers on top. This leads me to the other laws that govern stratigraphic facies. These other laws are cross-cutting relationships, included material within the beds, the law of lateral continuity, and the law of original horizontality. First, let's look at the law of lateral continuity. This law states that the stratigraphic layers of sedimentary rock will always be originally deposited flat, and it isn't until later deformation events that cause rotation or movement of the flat layers of rock. The law of original horizontality states that the layers of rock are continuous in sequence unless an external body prevents deposition or external force is enacted after deposition takes place. This can include erosional processes that remove layers of rock. Looking at Crustle, because of the flat-lying layers of rock on his home, we can assume there was no after-deformation event after sediment deposition occurred. For cross-cutting features, this can be a fracture within the rock, a vein of silicate material moving through, or a dike of volcanic rock. All that is really needed is a feature cross-cutting the various layers of beds. The law behind this is that any of these cross-cutting features must be younger than the sedimentary beds they cut, as a fracture cannot exist before the rock. For the law regarding inclusions, this can include clasts of rock within the stratigraphic layers as seen in the layers of Crustle's back. These clasts are made of reworked material from older layers during settling of younger beds, and vice versa. Now, let's give our friend Crustle a closer look. As mentioned previously, we'll just assume that the way up direction of Crustle's layers is the normal bottom to top. Crustle doesn't appear to have any cross-cutting features, so we don't need to worry about that either. And looking at the included clasts within the layers of Crustle's home, let's first determine how many beds Crustle has on its back first. Using the color of the layers, let's assume that the sand parts of the beds are the yellow rock, and the mud silt parts are the gray and dark gray layers of the rock respectively. In essence, the largest grains are the yellow areas, the medium-sized grains are the gray areas, and the smallest grains are the dark gray areas. Knowing how different grain size settle based on their size, we can see Crustle has at least 5 beds with a large main bed in the middle consisting of the 3 layers of grain sizes, with 3 beds below and 1 on top. Now that we know how many beds Crustle has, let's look at the clasts. We can say that this clast came from this bed, these clasts came from this bed, these clasts came from this bed, and these clasts were just incorporated into the bed during deposition. Thank you, Crustle. Now that we know what flat-lying bed forms look like, let's talk about bedding unconformities. Unconformities are contacts between different rock units that show a break in geologic time. I stated before that stratigraphy is one of the best indexes of geologic time, and this uses the fossils that are trapped within these rock units. We know where a majority of fossilized early life sits on the geologic timeline, so using these fossils we can confidently age date these rock units. These fossils are known as index fossils and are used because of how widespread they were across the planet during a very short period of time. Some of the more common index fossils are trilobites from the Cambrian period and ammonites for the Jurassic period. Getting back to unconformities, there are 3 main types. A disconformity, where sequential rock layers have a break, usually due to erosion at the surface with more sedimentary layers deposited on top. An angular unconformity, which is similar to a disconformity. This is where layered rock unit experiences a deformational event, changing the orientation of the layers before the erosional event and having flat-lying layers deposited on top. And for the third, we have a nonconformity. These are where layers of sedimentary rock are deposited on top of an igneous or metamorphic rock. With Crustle, we don't see any unconformities with his layered house, which is unfortunate because an angular unconformity Crustle would be pretty cool. In essence, these unconformities really just show that sediment deposition isn't continuous over time, and breaks in sediment deposition are needed for these unconformities to form.
Hey, how's it going, everybody? Welcome back to my university. Today we're actually in my structural lab, and today we're going to be taking a look at some of the stratigraphy I've been mentioning earlier, with some deformed stratigraphy. We're going to look at some flat stratigraphy. We're going to look at some of the bed plans, some of this cool stuff. And right in front of me, you're probably thinking, what is this big guy right here? So this is, based on our law of original horizontality, our beds are going to be flat, nice and flat, much like this guy right here. A little hard to see, but I'll give you a close-up. So these beds are originally just deposited flat, much like this guy right here. And once these beds go through a process of deformation, forces are coming and pushing the rock together, kind of pushing it like that, on this end and this end, pushing it like this. You end up with things that look like this, and this little guy right here. So this was originally flat, but as you can see, it kind of comes down like this. This bed comes back up, comes back down. That's what's known as folding. This is when 2 forces are coming and pushing the rock together, much like an accordion. You think of it like an accordion. And there's this little guy right here, kind of coming down, and up, just like that. Not as extreme as our big sample right here, but this is another deformed bed. And so this guy right here, this is actually our angular unconformity that I was mentioning. So as you can see, the bed, there's flat beds on top, but underneath these bed planes that have been folded and deformed, much like what has occurred here. So what happened was these beds below were deposited, solidified, became the rock, and then forces came in, squeezed the rock together, which is why we've got a little accordion shape down below. And then as that happened, sometime after, who knows when, the flat beds on top were then deposited. We know no other deformational processes happened because these beds are still flat. Yeah, this is stratigraphy, the many vast science behind it, but these are what beds look like.
Now, let's highlight some of the more important points. Sedimentary rock is made from the accumulation of pre-existing rock material, and this accumulation forms beds, which then sort themselves based on grain sizes. There are a few laws to help us understand stratigraphy, with the main one being the law of superposition, that states that the youngest layers of rock are on top of the older layers. As well, we have index fossils and sediments that can help determine rock ages and are one of the best indexes for geologic time. And layer unconformities exist, showing there can be breaks in the geologic record. Now, let's talk about shiny crustal and how we can use this green-colored crowd to talk about uranium deposits. I always thought to myself, just looking at crustal, and it screams radioactivity to me. And as it turns out, there are actually two different types of uranium deposits hosted in sedimentary rock, those being paleoplacer deposits and sandstone-hosted deposits. Let's start with paleoplacer deposits, as they're relatively more simple. Paleoplacer deposits are ones that have formed through the buildup of sediments over time and commonly host gold as well as uranium. These sediments have eroded away from specific rock which hosts the elements themselves and accumulated them during deposition because of their similar densities. Because the heavier elements remain and the lighter elements are swept away, there's a high enrichment of gold and uranium in these deposits. Similarly to how beds form, the uranium will accumulate in layers as deposition occurs over time. We can see an example of this with the Elliott Lake Blind River deposit just east of Sudbury, Ontario. This sedimentary rock is a part of the Huronian supergroup, a large collection of sedimentary rock in what's considered quote-unquote northern Ontario. As you see here, this deep depression that hosts the Elliott Lake uranium, the only part of the Huronian supergroup with this mineralization, collected the dense elements during deposition, forming our paleoplacer deposit. Now, for sandstone-hosted uranium deposits, there are actually two different subtypes for this deposit, but form in very similar circumstances. So we'll focus mainly on the tabular variety of sandstone-hosted uranium. Uranium is transported in geothermal fluids from the crust as U6+, which interacts with the sandstone beds. It's important to note that for uranium, the two main minerals for mining are uraninite and pitchblende. Uraninite is the more reduced version of uranium, thus giving it a 4+ charge, where pitchblende is the more oxidized version of uranium, giving it a 6+ charge. For uranium to be profitable in mining, uranium 4+ is the preferred element, as there are less oxygens involved in its complex. The solution transporting uranium 6+ will enter into the sandstone, and the beds in the sandstone will confine the solution, trapping it in the rock. Within the sandstone, there are other complexes such as carbonaceous material, pyrite, H2S, as well as hydrocarbons. Really anything with carbon and sulfur, as they are the reducing agents, which reacts with the uranium 6+. Uranium then will precipitate and form minerals because of this reaction, and the uranium 6+ is then reduced to uranium 4+. We can also see a color shift in the sandstone, where the sandstone will turn red as oxidation occurs. We can see this in the Wyoming uranium province, where many layers of layered sedimentary rock contain these favorable sources of uranium. Thanks for staying to the end of my video. I'm hoping to make this into a series of videos around the same concept, using Pokemon to help explain different aspects of geology and different geological properties. For this one though, I feel I may have went a bit too scientific with some of my information, so please let me know if it was too much or not enough, because I could easily do more. I really enjoyed making my video on the geologic interpretation of the Sinnoh region, and I loved the wonderful reception to it, so much that I wanted to make more geology Pokemon videos. I won't spoil my next video topic, but it's around a similar theme as this one, so to get you all thinking, here's a hint. Leave a comment down below if you learned anything today, and I hope to see you in the next one. Bye. Oh, and Dallas, when are you gonna hunt for shiny Dwebble number 7?